Hello everyone, this is part 3 of the solve questions of 17 December 2018 which was asked in ISRO Scientist Engineer computer science question paper. In this video we will be discussing about the questions from 22 to 31. Let's move on to the questions. Okay, the 22nd question is, consider the grammar with the predictions S is equal, we have three predictions, that is S is equal to ASB, S is equal to SS and S implies epsilon. Here we have three predictions in our question. Okay, 1, 2, 3. Sorry, 1, 2 and 3. We have three predictions in our question and we have to tell whether it is context free or linear, or it is context free or linear or not. So what is context free? Okay, the grammar is context free if the left hand sides of all the prediction contains exactly one non-terminal symbol. So this is the left hand side of our prediction, it is the right hand side of the prediction, and S is the non-terminal here and A and B are terminals. So the left hand side contains exactly one non-terminal. Okay, so our grammar is context free. So the answer can be either C or D. Okay, now what is a linear grammar? Let's see. A linear grammar is a context-free grammar that has at most one non-terminal in the right-hand side of each of its prediction. That is, it must have, it can have at most one non-terminal. Okay, here we are having one non-terminal. It's okay. This prediction is fine. Okay, this prediction isn't, it's context-free. Here we don't have any non-terminal. This is okay. The last prediction, third prediction is also linear, sorry. But the second prediction, that is S implies SS. Okay, we have more than one non-terminal in the right hand side. So this is not linear. So due to the third prediction, our grammar is not linear. So our answer is C. That is, it is context free, but it is not linear. Next. Identify the language generated by the following grammar. Okay, we have to identify that which of these languages is generated by the following grammar. So let's take the first prediction, that is S is equal to AB, and I'll try to expand it in the bigger way. That is, out of these two, this is the bigger one. So first I will try this, and out of these two, this is the bigger one. So I'll replace A by alpha A B and B by B B. Okay, so this is my grammar. So after that I'll try to replace this A by epsilon. So it is A, B, B, and this B by this B. This B. So what I'm having is, it is A to the power M and B to the power N. It is something like this, and N is greater than M. Okay, so N is greater than M is there. So it is like everywhere N is greater than N and M is greater than 0. Everywhere it is there. Okay. Now I'll try to take the least one. That is S is AB. It is the first one. You can take it like this. And for A, I'll be writing epsilon. So it is the least one. And for B, I'll be writing just B. Okay. So if we can write like this in the form of A to the power M, B to the power N. If you want to write it like this, then we have M is equal to 0, okay, and N is greater than 0 and N is greater than M. So we have two things over here. Okay, so we can combine like what? M can be equal to 0. For here M is greater than 0 and N is greater than 0. If we combine both these things, so what we would be having? We would be having like M is either greater than or equal to 0. M is equal to 0 and M is greater than 0. Okay, and N is always greater than M. So this should be my condition for A to the power M, B to the power N. Okay, let's check where it is. Okay, N is greater than M. N is never equal to M. Okay, it would be always. So this is false. N is greater than M is okay, but here the equal to sign is not there. Okay, and here we have N is greater than equal to M, so it is not right. Here the equal to sign is not there, but here N is greater than M is there, M is greater than equal to 0 is there, but here in both cases they have written M. It may be some printing mistakes, so here it should be N. So our option can be D if it was replaced with N. So in the ISRO question paper, this question was not included in the calculation. So it should be D, but in place of M, it is maybe a typing mistake. It should be N. So the answer is this, D1. Okay, so next question. Let L1 be a regular language. Okay, I'll write L1 is regular, L2 is deterministic context free, okay, and L3 is recursively enumerable but not recursive. Okay, L3 is recursively enumerable but not recursive. So which of the following statements are false? Let's see the first one. We have L1 is regular language. So if L1 is regular, it would be recursive, enumerable, or it would be recursive. Okay, let's see. L1 is recursive because every recursive language is decidable. So L1 is recursive, enumerable also, it is recursive also. Okay, but L3 is only recursively enumerable, but it is not recursive. So it is L3 is undecidable. And intersection of a recursive language and a recursive enumerable language would be recursive enumerable. It won't be recursive. So A is false. Okay, so we got the answer in the first statement itself only, but we would be seeing all the other statements also. Let's move to the second. We have L1 intersection L2 and intersection L3 is recursively enumerable. Okay, if it was given L1 intersection L3 is recursively enumerable, yes it is, because L1 is regular language and all regular language are recursive also and recursively enumerable also, and L3 it is already given recursively enumerable. Okay, so intersection of two recursive enumerable languages recursively enumerable. Now what about L2? L2 is given it is a deterministic context-free language. So all the context-free languages are also recursive enumerable. Okay, L1 is regular, so it is recursively enumerable. L2 is deterministic context-free language, so it is also recursively enumerable. And recursively enumerable language are closed under intersection. So these three languages all are closed under intersection. So it is true. Next. See, it is given L1 union L2. L1 is regular, so it is context free. L1 is regular, so it is context free. L2 is deterministic context free, and every deterministic context free language is also a context free language, and all the context free languages are closed under union, intersection and clean star. So these two are context free languages and they are closed under union, so it is also true. Okay, next is also true because deterministic context languages are closed under union, intersection and clone star with regular languages, and every DCFL is also a context free language. So it is like L1 is context free because it is regular, and L2 is deterministic context free, so it is context free, and context free languages are closed under union, intersection and clean star. You have to remember this. So this is also true. So in our question it was asked which of the following statement is false. So answer is A, that is L3 intersection L1 is recursive. It is not recursive, it is recursively enumerable. Okay, next. Let a to the power p is a prime number, then which of the following is true? Okay, we have to see whether it is a context free language, it is a regular language, or it is accepted by a Turing machine. Okay, so let's talk about these two, that is context free and regular. Let's check whether they are true or not. Okay, for any language to be regular or context free, it has to have some pattern. Okay, suppose we have even number of A's. So we have a single A, we have double A's, sorry, we have 2 A's, we have 4 A's, we have 6 A's. So there must be a pattern, that is these 2 A's are repeated 2 times here, these 2 A's are repeated 3 times here. So whenever we can identify some pattern, then we can say that our language is regular or it is context free. So for both the things, for being regular or for being context free, there must be some pattern. But in case of prime number, we have no pattern. So the both B and C is not true. Now what about the Turing machine? Yes, it can be accepted by a Turing machine, because we can write an algorithm. We all have written programs on calculating prime. Okay, so there exists an algorithm. So whenever there is an algorithm to solve any problem, if we can write a program for some problem, then that problem there must exist a deterministic Turing machine for that problem. Okay, and if we have a deterministic, here we have no bound for prime. We have set p is prime, we have not set any bound. So just p as a prime number, and there is no bound on the length, so we need infinite amount of space. So Turing machine can be used to recognize it. If the space is finite, then we have deterministic Turing machine to recognize it. Okay, for finite space. For finite space, we would be using deterministic Turing machine. For infinite space, we would be using Turing machine. So it is not accepted by a Turing machine. No, it is accepted by a Turing machine. So it is neither regular, true, it is nor context free, but can be accepted by a Turing machine. So our answer would be D. That is, a to the power p is a prime number, is accepted by a Turing machine. So answer is D. Let's move to the next question. Which of the following are context-free languages? We have given 3 languages and we have to decide which of them is context-free. So for context-free, if we can solve the problem, solve the problem using a single stack, then those languages are context-free. Okay. Now let me see for language A, if we have a stack, okay, what I'm doing is, we have to solve a to the power n, b to the power n, a to the power m, b to the power m, and there is no connection between n and m. Means these two things, n and m, are independent over here. M is greater than equal to 0 and n is greater than equal to 0, and there is no connection between m and n, both are greater than equal to 0. So now what I'm doing for here is, I will be pushing a's onto the stack. Suppose I have pushed n a's onto the stacks, okay, and whenever there comes a b, so what I would be comparing? I would be comparing this a and b. Okay, whenever there is a b, I would pop that a, because these both are equal. These both numbers are equal. So whenever there is a, I'll pop b. So sorry, whenever there is a b, I pop a. So for 1b, for 2b, for 3b, for 4b, up to nb. So this is similarly, after popping all b's, I'll put m number of a's. Okay, and whenever there comes a b, I'll pop all a's again. So both these two things are solved by using single stack. So this language is context free. So A should be in our answer. So our option C is almost cancelled and option D is almost cancelled. Now we have only 2 options, A and B, and we are going to check for B. Okay, for B, suppose I have a stack. Okay, I'll put m number of a's. Okay, but after A I have B, but I don't know what is n. N can be equal to m, n can be anything, because there is no relation between n and m here. So I don't know how many number of b's would be there. So I would be using a different stack for B. Okay, so this problem cannot be solved by using a single stack. So it is not context free. Okay, so B is not context free. So this option is also cancelled. Our option is B. Our answer is B. C should be context free. Let's check how. C is context free. We have, if I write m is not equal to 2n, what does that mean? That is, m is not even, m is odd. Okay, so now what I am going to do is, I'll put m number of a's here. Okay, and whenever a b comes, I'll pop odd number of a's. Okay, so by using a single stack, we can solve this grammar. We can solve this grammar. So this isn't context free. Okay, so answer is B. That is, only A and C are context free languages, whereas B is not. Okay, next. Let S be a NP-complete problem. Okay, you have to remember this. S is NP-complete, and Q and R are other problems. They are not NP. Okay, they are not NP. Q and R are not NP, but S is an NP-complete problem. And Q is polynomial time reducible to S. So Q is polynomial time reducible to S, and S is polynomial time reducible to R. Okay, we don't know anything about Q and R, but we know that S is NP complete. This is our question. S is NP complete. Okay, now which of the statement is true? Let's take over the first statement, that R is NP complete. It is incorrect because R is not NP, because it is given that it is not NP. Both R and S are not NP, and NP complete problem has to be in both. It has to be NP and NP hard. Okay, if a problem is NP complete, that means it has to be NP and it has to be NP hard. So it is false. Second, R is NP hard. We know that R is not NP, but yes, it is NP hard because there is a polynomial time reduction from NP complete problem to R. Okay, NP complete problem S is polynomial time reducible to R, so R is NP hard. That is, R is as hard as S, so R is NP hard. So this is true. So this is our answer. Let's check others also. Q is NP complete. No, Q is not an NP complete, because to be an NP complete, it has to be NP, it has to be NP hard. Okay, Q is not NP. That is mentioned in the question. Whether Q is NP hard or not, let's see. No, it is not, because Q doesn't have any polynomial reduction from any NP complete problem. Okay, so that is because Q is not an NP. That is for 3. Okay, it is not NP complete. And above 4, because there is no NP complete problem that is polynomial time reducible to Q. There is no problem which is polynomial time reducible to Q. There is no NP complete problem which is polynomial time reducible to Q. The Q is not NP hard. Only R is NP hard. So answer would be B. R is NP hard. Okay, next. Okay, the number of structurally possible binary trees with 4 nodes. We have a formula for this. Number of binary trees which are possible are, the formula is 2n factorial. Here n is 4 upon n plus 1 factorial n factorial. Okay, so it is 2 4 is 8 factorial, 4 plus 1 it is 5 factorial into 4 factorial, and we can further reduce it to 8 7 into 6 into 5 factorial upon 5 factorial into 4 into 3 into 2 into 1. Okay, 5 is cancelled. It is 4 2s are 8, 8 is cancelled, 3 1s are 3 2s are 6, it is 14 should be our answer. So answer is A. Number of, you have to remember this formula. It is 2n factorial upon n plus 1 factorial into n factorial. Okay, it is 14 is the answer. Okay, next question. Okay, using a public key cryptography. So here you are having a public key cryptography. X has a digital signature sigma to a message M and encrypts and send into Y. Okay, see, first the digital signature is added. Okay, so how the digital signature is added is, X would be using his private key. Okay, for digital signature, first X adds the signature. So X private key would be used first. Okay, and sends it to Y where it is decrypted. So first X private key would be added. Okay, and after that, using Y's public key, it would encrypt the message. Okay, this is at the sender side. Okay, at the receiver side, see, first this is done first, and after this is the cover is like, it is X private key which is covered by Y's public key. It is like this. So first the outer cover has to be removed. So we would be having Y's private key first. Y should be using it private key, and then after the outer cover has been removed, it would be using X public key. So let's see what X private key should be the first one. So X private key, it is all X private key. So it is the first one, followed by Y's public key. X private key followed by Y's public key. Okay, these two can be the answer, and then Y's private key. So it is the answer. So our answer is C, followed by X public key. The answer is C. Okay, next question. Which of the following are used to generate message digest by the network security protocols? So there are four protocols given, four methods given. So let's see what are they. SHA is a secure hash algorithm, SHA 2256, and it is a cryptographic hash function, and it produces a message digest at 256-bit hash value. So yes, SHA is used because it is used to generate message digest. Next, AES and DES. Okay, AES and DES are symmetric key algorithm. Both are symmetric key algorithm for encryption for electronic data. So these two are not used. So P and S is option. S is it is specially for message digest. MD5 is widely used for cryptography function that produces 128-bit hash value, that is a message digest. So answer is SHA and MD5. So P and S should be the answer. It is A is the option. It is the answer. Okay, next, in IPv4 addressing format, the number of networks allowed under class C is, okay, so we will be talking about three classes here, that is class A, class B and class C, and it is IPv4, so it is a 32-bit, or we can say it is 4 octets. Okay, so we would be having 4 octets for all here, 1, 2, 3 and 4. Here also we would be having 4 octets. 2, 3 and 4. Here also we would be having 4 octets. Okay, and for A, the first 8-bit is the network ID, and for B, the first 16-bit is a network ID, and for C, the first 24 bits is a network ID. Okay, so we have here 8 bits, here 16 bits, here 24 bits. Okay, but for class A, the first bit is always fixed. So what number of networks allowed would be, we would be minusing the first bit, that is 8 minus the first bit, that is 2 to the power 7. For class B, the first 2 bits are fixed, that is 1 and 0. The first 2 bits are always fixed. So we would be subtracting 16 minus 2. The first 2 bits we would be subtracting. So it is 2 to the power 14 would be the number of addresses for class B. And for class C, the first 3 bits are fixed, that is, it is always 110. So we will be subtracting the 3 bits, that is 24 minus 3. It would be equal to 2 to the power 24 minus 3, which is be equal to 2 to the power 21. So answer should be 2 to the power 21 for class C. Okay, this is D, 2 to the power 21. Okay, this is the answer. Next question. Next. Okay, this was all about the solved question papers for these questions. If you like the video, please subscribe our channel, and thanks for watching.